Okay, we're going to link the change in Gibbs free energy, delta G, to our study of equilibrium. So previously covered, we've talked about the change in free energy, delta G, and that it determines whether or not a reaction is overall spontaneous. It's based on considering temperature, change in entropy, and change in enthalpy. And delta G can be considered, or another way to talk about it is to call it the usable work that is either released or absorbed by a given process. So the following, just to review, the more negative a delta G, that makes a reaction more and more spontaneous for the forward reaction. And so now that we're considering reactions that go forward and backwards, that means the more spontaneous the forward reaction, the more non-spontaneous the reverse reaction. Increasingly positive delta G values mean that the forward reaction requires more and more input of energy to take place, so it's more and more non-spontaneous, while the reverse reaction would be more and more spontaneous. A couple of reviews. There we go. Move that. So the total G, which we can't calculate directly. We only ever calculate delta G, but theoretically you can consider the total amount of usable energy that's stored up in reactants. That we could label that as G of the reactants. And the products also have a total amount of stored usable energy, which we could call the free energy of the products. And if we subtract the two, products minus reactants, that's how we get the delta G. And we've drawn diagrams like this before, usually for potential energy or enthalpy. We've labeled the y-axis, but we can also do the same thing for Gibbs free energy. And so they look just like enthalpy level diagrams where you've got your starting amount of products and then reactants, and this is the change. So regardless of whether or not the process is spontaneous or not, both reactants and products do contain some usable energy. So like even though in this first reaction, which is a spontaneous reaction, the products contain less usable energy than the reactants, which is why the change is negative, and there's a release of energy to the surroundings. It's not that the products contain nothing. They still contain some usable energy. It just happens to be less than the reactants. And the same thing here. The reactants in a non-spontaneous process still contain some usable energy. It just happens to be less than the products. And as any reaction spontaneously takes place, we know that the reaction releases energy and does work. So just to point out something, whenever we have calculated delta G, we've always calculated it based on there being going from 100% reactants to 100% products. So all those delta G calculations where we do products minus reactants, or where we use the delta H minus T delta S equation, all of those factor in the number of moles of products and reactants, and they are calculated theoretically based on a total 100% conversion. So I've tried to represent that in this diagram. At the beginning, that line that we draw represents the total amount of free energy stored in all the reactants, 100% reactants. And at the start, there's nothing in the products. I've drawn this line just to show where we're going to go to, but imagine it's not there. At first, you only have it as reactants, and when the reaction is done, there's only now this much stored energy as products. The reactants are now all gone, and so the difference in what you started with and what you end with, that's the change. And so this represents a spontaneous reaction. But if you actually consider what would be happening over time, so if you start off with this red line, which represents the total free energy if we've got 100% reactants, as the reactants start to get used up, the amount of free energy that's in that reactant form is going down. So that starts to decrease. And as soon as you start making products, there starts to be some free energy stored in this product form. Now, the rates aren't exactly the same, so you don't lose X amount of energy here and gain it there at the exact same rate, because the way we've represented it, some energy is also being lost to the surroundings as this usable work being released. But for every amount of energy that is lost, some energy is also then stored back up in as products. And so there's always going to come a point in any reaction, if this is the case, where before you get to 100% product, there's going to be a point where the total energy of the reactants that's left in the reactants that still haven't reacted is going to be equal to the amount of energy in the now formed products. And I've tried to represent that with this diagram here. So as this one falls, and as the amount of energy in product form rises, there's got to be a point where they equal. Okay? There has to be a point where the amount of energy stored in each is the same. And at this point, if you make any further changes in the amounts of reactants or products, it's going to require a net input of free energy. It's a positive change in delta G, which we know shouldn't really happen spontaneously. That requires an input of work, right? So if you're at this point right here, if you want to make any more reaction happen, that means that the, can I still shrink this? I don't know if I can still shrink my little rectangle. Well, the rectangle would shrink, right? So if this goes down anymore, right, so that would still be releasing energy. However, this rectangle would be growing, right? And so if you make the reaction happen anymore, you're actually putting in extra energy to form this new amount of product. So I'm going to undo those changes. See if I can regrow my rectangle there. Okay. So although it's kind of a weird new concept to consider, the actual point at which you have the minimum total free energy in the system, the total G of the system, it actually exists wherever the amount of free energy in reactant form that's still left over is equal to the amount of free energy that's in product form that's been made so far. And so this means that for any reaction, the lowest total free energy for that system is going to occur at an equilibrium state, a state where you've got some reactants and some products both present in the reaction mixture. So it's kind of a new concept, but again, the delta G that we would calculate from our equations is the change between this red and this blue. But that's a theoretical calculation based on 100% reactant to 100% product. And so in reality, the change may be a little bit different than that, because the reaction will likely not go to completion. It's going to find its lowest energy state, its most stable state, when there's some reactant and some product. And so at equilibrium, we can say that the total free energy of reactants equals the total free energy of the products. And therefore, at that point, the delta G is equal to 0. And it's not going to really net proceed or go back. And that's why it's equilibrium. You have both rates are equal and opposite at that point, so there's no net change. Just to point out, just because they have the same amount of total free energy, it does not mean we have the same moles or concentrations of reactants and products, because the identity of the reactants and products is going to be different. They have different amounts of stored energy per mole. So this is not trying to suggest that you have to have equal moles of reactants and products, but the amount of stored energy in reactant form and product form is going to be the same. So this also means that even if you have reactions that are technically non-spontaneous, as they're written, positive delta Gs, there may still be some minimum delta G for the minimum G for the system, which involves a tiny bit of reactant reacting and a tiny bit of product forming. So even if you get a positive delta G, there may be some sort of an equilibrium state that can develop. It doesn't have to, but it is theoretically possible, because as some of the reactants get used up, it may actually lower the total amount of free energy of the system. So the summary is essentially this, that for any type of reaction, there exists a minimum total free energy for those reactants and products for that system. And wherever that minimum is, that's where the reaction is going to find its equilibrium. And so there should be a state of equilibrium where there's some products and some reactants present, and that's where the overall free energy will be at its lowest. And this is when the free energy of reactants and products are equal, though not their concentrations or their moles. The more negative the change in free energy for the forward reaction, so like one like this, the closer that minimum is going to be to the products, to having mostly products. So that implies that in a reaction like that, with a big negative delta G, you're going to mostly have products at equilibrium. We would say the position of equilibrium is far to the right, or it favors the products. If you have a reaction where the forward reaction has a positive delta G, the more positive the delta G, then the closer and closer the minimum will be to having all reactants. And so that equilibrium would lie far to the left and heavily favor the reactants. And so if delta G is not too big in either direction, if you have kind of a small delta G value, somewhat close to zero, then that implies that there's probably going to be a considerable amount, a measurable amount of both reactants and products at equilibrium. So we can sort of relate delta G now to Kc because they both imply something about the position of the equilibrium. So if you have a majorly positive delta G, a non-spontaneous reaction, that means that the position of equilibrium lies very far to the left. And that also means that the Kc value is going to be much smaller than 1. I think my Kc's here are incorrect. Whereas if you've got a negative delta G, that implies a very spontaneous forward reaction, which means the equilibrium is going to lie far to the right, and Kc should be large. And if you've got a delta G close to 0, then that implies that the position is somewhere in the middle. We've got a considerable amount of reactants and products, and that gives you a Kc near 1. So therefore, there must be a way to relate delta G to the value of Kc mathematically. It seems like they are somehow related. And sure enough, they are. It's been determined, an equation that's in your data booklet, that the relationship between the free energy change and Kc can be quantified like this, where delta G is the free energy change, R is the ideal gas law constant, T is the temperature in Kelvin, and K is the equilibrium constant. Ln is the natural log. The main thing to watch out for with this equation is that delta G's are generally listed in kilojoules, while R is listed with joules as the unit. And so you're going to have to do some sort of conversion with 1,000. So you either have to divide R by 1,000, or you've got to multiply delta G by 1,000 to make the energy unit consistent. But this equation allows the IB to test you on, can you go from a delta G value to an equilibrium constant, or can you go from an equilibrium constant to a delta G? If you know how to use natural logs, and you have your calculator, this is a fairly simple calculation to do. You just have to know which equation to use. And so we'll do some practice in class, but that's kind of all there is to it. Either you're going to be given delta G, or you calculate it on the test, and then you can use it to calculate a K value, a Kc value, or you can be given a Kc value, plug it in for K, and use it to calculate something about delta G, and then be asked a question about spontaneity or the position of equilibrium. And so that is the incorporation of our concept of spontaneity and delta G, and relating it to how things can find their minimum free energy for the position of equilibrium.